Okay, I think we're recording. All right, I think we are finally recording. So welcome everyone to this SI session. Excuse me. And looks like I got this little camera set up from IT. Thank you for them. And so I think it'll be easier to actually see my writing versus the chicken scratch on the virtual board, right? So, okay. So really, just want to go ahead and walk through some of these ALEKS problems you're doing. I know I did say in the past that I kind of tend to stray away from those, but this one's a little specific, right? It's pretty difficult, and it's honestly probably the hardest one you're going to have to do in this class. Okay. So let me get some writing utensils. Okay. Hello. We're good. So, put this on. Okay. We're back in business, ladies and gentlemen. Okay, so I'm actually gonna. So it's a little difficult because I gotta like switch screens a lot. It's definitely like kind of strange. Oh, I guess I can do multiple. Or it says I could, but I don't. Okay, I can only do multiple of the basics. So, alrighty. So let's get up ALEKS here, and let's do it. Okay. Okay. So I'm gonna pretty much do the one that everyone's like, they're like, it's insane, and it kind of is. It's actually, I used to have trouble on this all the time, even before I became your SI. But don't let that worry you. I know how to do it. Just takes a little time, you know. Alrighty. So here it is. So I have like the ability to look at the explanation. Explanation is actually, I can't say it's really bad because it's actually quite okay. Especially because this one's a little difficult, right? So let's just kind of run through this, okay? So we're at a festival and we have some spherical balloons and they give us the radius, okay? And they're to be inflated with hot air and released, okay? So we have air at the festival, of course, and it's in the air, right? It's 25 Celsius and it has to be heated to 100 Celsius to make the balloons float, okay? So, but we do have 1 kilogram of propane. So that's like the fuel, right? And we can burn that to heat the air, okay? And so we're wondering what's the max number of balloons that can be inflated with hot air, okay? They give us some data. So for instance, we have specific heat capacity of air, the density of air at 100 Celsius, the density of propane at 100 degrees Celsius, and this formation enthalpy, that's the same thing as enthalpy of formation of propane, okay? And that they give us this value, okay? And it says other data you should need can be taken from the ALEKS data resource tab, okay? So let's kind of walk through this. I'm going to share, new share, enhanced. Okay, so definitely makes me only look at this. I wish I can, like if I hit escape, it just won't work. So sorry, it looks like we're only gonna have to do this. So tell you what, let me, that. Oh, wait a minute, maybe. Okay, I'm holding control, but I don't know what they mean. Sorry, folks. Okay. So let's just I'll write down the details, okay? So we got a spherical balloon with a radius of 200 centimeters. We have a air temperature of 25, so that might be pertinent. We'll see. Usually what they give you is, and that has to be heated up to 100. So it has to go up to 100 degrees Celsius to become usable for the balloons to make them float, right? We are given 1 kilogram, 1 kilo of propane. That is a chemical. Okay, and we can burn that, and they give us the formula, C3H H8. Okay. All right, and they're saying find the max number of balloons that could be inflated. Find max of balloons. Okay. All right, they give us some data. I'm actually going to take a picture with my phone, so that way I don't have to keep clicking back and forth. And again, that was all the specific heat capacity and all that jazz, you name it. Okay. Okay, let me scroll down. Okay. Okay. We are in business. We are in business. Okay. Screen share. Second camera. Switch camera. All righty. Here we go. You guys ready? Got 2 markers here. Okay. So we are told that we have the balloon and its radius, right? You can really think of that as, it says spherical on ALEKS. It's a spherical balloon. So that tells us something, okay? So imagine we have a spherical balloon. Okay, and it has a radius. So really, if thinking of a circle, really it's a sphere, right? But thinking of a circle 2D, a radius is really half of that circle, okay? I know that looks like more, I just drew it kind of oblong, but it's a circle, and we're gonna go from the middle of the circle to the end, okay? That is the radius, and the radius we're told is 200 centimeters, okay? So that's one piece of information, okay? Now here's kind of the deal, okay? Ultimately, we're told to find the max number of balloons that we can fill, right? So evidently, we're kind of going to need to know the volume of the balloon to fill, okay? So we're going to need the volume, okay? Now, as it turns out, the volume of the balloon, and I say volume, we have to know volume because obviously we have to fill it with a certain amount of hot air such that the balloon can be inflated all the way and actually float, right? Okay, so the volume has to be, or really the volume of a sphere, because this is a spherical balloon, is 4/3 pi r cubed. So that's the formula for a sphere, okay? All right, so now what we can actually plug in some numbers here to get the volume of the balloon, okay? So the volume is going to be 4/3 times pi. Now pi really is something you want to press into your calculator because it is a constant, right? So you don't want to just type 3.14. You want all those significant digits or whatever you call them. Okay. Then we will have the radius. That's with r's, 200 centimeters. Now, first of all, you're probably like, well, wait a minute, don't we need meters or something like that? Well, remember, centimeters cubed, 1 centimeter cubed equals 1 milliliter exactly, like on the dime, okay? So really that's probably going to be useful for volume, right? Okay, because we usually work in milliliters anyway, okay? Not so much the other meters cubed or whatever, okay? So we're going to simply multiply by the 200 centimeters, cube it, okay? And let's find out what we get. Sorry about the lighting if it's bad, it's kind of in the way, I guess. Sorry. Okay, so 4/3. By the way, what I just did is you don't really have to do anything fancy. On this calculator, you can press alpha and then this y equals button, and you get a little fancy menu. And then if you just hit either 1 or enter, then you get like a fraction bar. So you can type 4/3 Okay, to get pi on this calculator, and you're going to want your calculator to have pi. Technically, if your calculator doesn't have pi, you can just type 3.14159. I guess that's enough digits. But let's go ahead and do them all. So we'll hit second and then up for this calculator. And then we're simply going to multiply by 200 cubed. Okay. All right. You could also do 4/3 and then multiply everything else. You usually want to keep fractions in brackets. Okay. So we're going to get a very large number. Okay. Remember, this is quite a large balloon. Okay. It's a hot air balloon, for goodness sakes, right? So it's going to have a pretty massive volume. Okay. So actually we get, so let's use some sig figs here. Sorry, scientific notation. So we can move the decimal back. Let's see. So you want to move it back such that you have one integer in the front of the decimal. Okay, always. So we're going to say 1, 2, 3, 4, 5, 6, 7. So we have 3.35 times 10 to the 7th, because that's how many decimals we moved it back. Hey, Natalie.
Hi.
Hey, yeah, I was pretty much just working on this hot air balloon one.
Okay.
Is that okay?
Yeah, that's the one I was having trouble with yesterday.
Okay, good. Yeah, most people were, so I'm gonna go ahead and continue. Alrighty, and I'm also recording it for everyone else in case I sound funny or whatever. All right. So anyway, to just review, Natalie, what we did was we're given the balloon. Okay, well, we're told it's a spherical balloon, right? Okay, and really a sphere, it's like that 3D circle looking thing, right? But we're told that it has a certain radius, okay, and we're probably going to want to find the volume of this balloon because we need to see how much hot air we can put into it to actually make it fly. Okay, so we're going to say volume of sphere is 4/3 times pi times r cubed. 4/3 and pi are just things in your calculator, so you can type 4 divided by 3, probably in parentheses in your calculator. That's often what you want to do. Okay, and then we got pi. And then the radius, we're going to keep centimeters because as it turns out, 1 centimeter cubed is literally 1 milliliter. So that works pretty well. Okay. All right, so now we're going to say the volume when we put all this in the calculator is 3.35 times 10 to the 7th. Okay. Because really, as you see here, we move the decimal place back 7 places. 1, 2, 3, 4, 5, 6, 7 until we get one integer in front of the decimal. And then we say 3.35 times 10 to the 7th. Okay. The units are going to be centimeters cubed. Okay. Why? Well, check it out. Centimeters. And then if you treat centimeters like algebraically, it's also getting cubed. Okay. So that's why we got that. Okay. Because 1 centimeter cubed equals 1 milliliter, you can think of this as milliliters as well. Okay. And it's going to be a large volume because, we're talking hot air balloon size, right? It's definitely pretty big volume. Okay. Alrighty. So now kind of the next thing we need to think about is probably in relation to how are we gonna, well, it's definitely kind of a lot of things going on. So that's probably the first thing you want to do is find the volume of the spherical balloon, okay? So we are given the fact that we have 1 kilogram, well, that's a kilogram basically, of propane, which is C3H8 chemical, right? So it's probably a good idea to actually look at that reaction, okay? Because that's going to generate the heat needed to heat up the balloon. So we're going to say C3H8 plus O2. Now, any combustion reaction is simply going to be, so when they say burning, that means we're going to have our hydrocarbon plus oxygen always. That will produce water. Pretty much all of this is gaseous. And that will also produce CO2. So you're always going to get water and CO2 as a product. You'll always have a reactant as O2 and some hydrocarbon like that. Okay. Sometimes this can have an oxygen, but in this case it doesn't. All right, we got to balance this, of course. So as it turns out, we have 3 carbons here. 1 here, we got to put a 3 for the carbon. Okay. I wouldn't do the oxygens first because there's just a lot everywhere. So that's why we did carbon first. Now hydrogen, looks like there's 8 on this side, 2 here. So we're going to have a 4 here, okay? Because that's going to be 4 times the 2, which gives us 8. Okay, so now it's equal on both sides, which means balancing. All right, as far as the oxygens, we'll check it out. We have the 4 also affects not only the H2, it's not always just 4 times the 2 H's, it's also 4 times the oxygen. So we also have 4 oxygens. And we also have 3 times the 2 already on CO2. That's 6 oxygens. Okay, add those together, you get 10. And really we're saying, what number here can we put to make 10 on this side, since that'll equal 10 on this side? I'm going to say 5, okay, because 5 times 2 is 10. Okay, that's a balanced chemical equation for the combustion of propane or burning of propane. Okay, and that is what's going to generate our heat. So one thing's for sure is we need to heat up a certain amount of air, right? Okay. So what I'm thinking, okay, is that remember in those calorimetry problems, we usually had a reaction and the reaction would let off heat into the water, okay? And remember, we would use this equation, Q equals M times C times delta T. I'm just going to refer to it as MCAT from now on, because the delta kind of looks like an A, right? So we use this equation to relate the mass of this substance, the specific heat capacity of the substance, and the change in temperature it undergoes. And this all is related to the heat energy, okay? Okay, so how much heat is released or gained, and that's usually in joules, okay? Now the thing is, that was for water. We had a reaction, it would release water to the surroundings. We would measure the water temperature to see how much heat went into the water, okay? And how much heat went into the water was the exact same amount of heat that came out of the reaction. So what we're going to do is we're going to be heating up the air, right? So we're going to be taking the reaction from the C3H8 and putting that heat energy into the air, okay? And that's why ALEKS gave us some information about the air, right? So let me get to my images here, because it won't let me, I have to go back and share it. It takes a while. So let me turn my brightness up. Okay, so sorry about the glare. I don't really know what to do. Basically, they'll give you the information, right? So they'll give you the specific heat capacity of air and the density of air and all that stuff, and density of propane, etc. Well, notice they give us the specific heat capacity of air. That's probably telling us, hey, we're going to use this equation to find out how much heat the air can absorb, okay? So really, this is about air. Okay? So evidently, we're going to need the mass of the air. We're going to need the specific heat capacity of the air, which we have. ALEKS gave it to us. And the change in temperature of the air. Okay. Alrighty. So evidently, we are trying to find out the max number of balloons, right? But let's think about the first thing is maybe not how many balloons, but let's just think about how much heat we're gonna, or really how much propane we're gonna need to actually get us to the amount of heat for one balloon. Okay, because obviously we'll need to produce this much hot air to make us a full balloon, okay, with that certain radius that we calculated, okay? So let's go ahead and think about this, all right? So the first thing is that we really want to see kind of how much heat energy this takes, right? And really, first of all, the mass of air. We don't really have the mass of air, right? ALEKS also gives us the density of air at 100 degrees Celsius, though, okay? And that's important because we're going to have to see, using the volume of the hot air, we can then find the mass from the density, okay? Density is a conversion factor. So in fact, let's do that. So we're finding mass of air, okay? We're going to take the density, or rather, let's multiply. So we're multiplying, so let's see. So we're going to say 3.35 times 10 to the 7th mils, okay? Okay, I just realized that ALEKS gives you units of density of air in kilograms per per meter cubed. Okay, so in all honesty, yeah, it looks like. Sorry, we're gonna have to go back a little. Okay. Ultimately, we're trying to find the mass of the air right now. We need that. We need the density of air at 100 degrees Celsius because this is all hot air, right? So this is the volume of hot air. Okay. We're going to need the density of the hot air and the actual volume of hot air. So maybe not mils, actually. Sorry. We're going to actually have to find the meters of it cubed because we're told. Sorry, hold on, Natalie. I got a message. Okay. You still there, Natalie?
Yes.
Okay. Sorry. So anyway, yeah. So we're curious about the mass of the air, right? So we need the density and the volume of air. Well, ALEKS gives you the units of the density of the air as kilograms per meter cubed. Okay. Evidently, we're gonna have to find. We got to match up units, right? So we're gonna have to find the units of the volume of hot air in meters cubed. Okay. So an easy way to do that is to simply convert the centimeters in the original equation to meters. And by doing so, we can say, well, you know what? That way we'll just plug in the meters here and it'll be cubed instead of having to convert centimeters cubed to meters cubed and then whatever, right? Okay. 200 centimeters. You can use a conversion factor here, okay? Centimeters will go on bottom to cancel. Meters will go on top. Centimeters is going to cancel on top and bottom, right? But we need to know that what centi means. Well, centi really means 100, okay, or 10 to the, well, rather it doesn't mean 100, I apologize. Really, it means 1 over 100 or 10 to the negative 2, okay? So technically, you could say 10 to the negative 2 meters is 1 centimeter. If you give the bigger unit the 1, then you can just say, well, you know what, the other one is positive. And so it's 10 to the squared centimeters versus meters, okay? So really, divide 200 by 100, and I believe that's 2, right? And then we're going to find our meters cubed. Right? Sorry, meters. Okay. Balloon's 2 meters. So guess what? In this original equation, we're going to say, you know what? Forget centimeters. Let's just plug in the original 2 meters. Okay. Do you have the same calculators I do, Natalie, or similar to it?
No, I don't.
Okay, that's fine. I explained that you probably, if that's in that event, you're probably going to want to put in parentheses your fractions just to be safe because of order of operations. Then you're going to want to use pi. If your calculator doesn't have pi, you can use 3.14159. Okay, and then multiply, of course, by the 2 cubed. All right, I get 33. So the volume, the new volume in meters, is 33.51 meters. Okay, cubed, meters cubed. It's cubed because remember that cube there will affect the meters side. Okay. So now we have our actual volume of hot air. Okay. So we can find the mass of the hot air by simply taking the volume and multiplying by the density. So the density of the hot air at 100 Celsius is given in ALEKS as 1.440 kilograms per meter cubed. Well, we can actually simply plug that in. Okay. Now, remember, density is a conversion factor, so you could have flipped it if we were asked to find something else, just letting you know that. Okay.
Wait, where'd you get the 1.440 from?
So ALEKS actually gives you the density of air. Oh,
Okay.
I'm sorry. That was the density of propane. I apologize. It's actually going to be 0.946. Okay. It's still in units of kilograms per meter cubed. So with that being said, let's go ahead and multiply. Meters cubed cancels on top and bottom. We're left with kilograms. So really it's the 33.5 times the 0.946. All right. All right. So that's our mass of air. Okay, we use the density as a conversion factor to say, hey, we're given we're trying to find the mass of air. Okay, that's in grams. We are given density, which relates kilograms in volume and relates mass and volume. And so we can multiply the density by the volume, cancel volume to get kilograms. That's our mass of air in kilograms. Now, the density or the specific heat capacity of air is actually given to us as 1.009 joules per gram degrees Celsius. Okay, so 1.009 joules per gram Celsius. Well, really, you got to have the same units, right? So we're going to have to convert from grams eventually. So really that's like saying you can put kilograms on the bottom, grams on top. Remember, give the big guy the 1, right? So kilo is bigger than gram. Okay. Kilo is also defined as 1,000 if you look it up. That's what kilo means. Multiply these. I guess you can move the decimal back or forward 3 places. That's the same thing. Just to show you here. 31700 grams of air. Okay. This is our mass of air that we'll need eventually. Okay. All right. Now, let's look at the change in the temperature of the air. Okay. So that's going to come from delta T is simply the temperature final of the air minus temperature initial of the air. So in general, delta means change in, right? So it's all delta is always the final minus the initial. That's not just for temperature. In this case, it's T. So we're saying the T final of our air, and it's air because that's what we're dealing with in our equation, minus the T initial of the air, the temperature. Okay. Now we're actually given both of these, right? Because they said the balloon temperature originally starts off as the final, or rather, I apologize. It starts from 25, the air temp that day, and we need to heat it up to 100 for the hot air for the balloon, okay? So the final is really the 100. That's our final temperature we need. So final first, minus the initial, which was 25 degrees Celsius, okay? I believe that's 75. Okay. Okay. Sorry about maybe I'll do that to make it more obvious. Okay. So guess what? That is the temperature, or rather change in temperature of our air. Okay. So guess what? Now we have everything for our equation. The mass of air, the specific heat capacity of air, and the change in temperature. So this will tell us how much heat energy the air has absorbed from the combustion of propane. Okay, so we're gonna say M, mass.
I can't see the paper.
Oh shoot, sorry. How about now?
Yeah, you're good.
Nice. Okay, so 317, or sorry, this is the mass of air, right, in grams, okay? Multiply by the C, specific heat capacity of air, which was given from ALEKS as 1.009 joules per gram Celsius. Okay. Multiplied by the change in temperature, which was 75 degrees Celsius. Okay. Let's cancel units. Grams cancels on top and bottom. Celsius cancels on top and bottom. We're left with joules. Okay. Multiply as so, like so. it's going to be a lot. It's a lot of heat energy we have to put into the air to make these balloons float. So joules is going to be, so let's use sig figs, right? Or scientific notation. We're going to go. So you want to move the decimal place such that there's one integer in front of it. So we're going to say 1, 2, 3, 4, 5, 6. 2.39, or rather, technically 2. Let's use some sig figs here. Let's say 2.398897.5 times 10 to the, we moved it back 6, right? So we said 1, 5, 6. That is our massive, or that is the amount of energy put into the air by burning propane. That much joules, okay? Now, this is for one balloon, right? Okay. Now the question is how find the max number of balloons, right? Now, first of all, we're given 1 kilogram of propane, right? Okay. So that's that. Okay. So really, we can use. So remember that? Do you remember that thermochemical stoichiometry where it's like you're given grams of a substance, and given the enthalpy, you can find how much heat is released for that gram of substance? You remember that?
Or barely.
Barely. It's fine. Yeah, so we can do that. Now there's a couple of issues here.
I
So,
thought I'll know, like once you start doing it.
oh, what's that?
I said I feel like once you start doing it, I'll remember.
Okay, sounds good. Let's change marker. Okay, so okay, there's our equation. Sorry, I'm just checking. Okay, so what we're saying is, well, if we found the enthalpy change of this equation, and it's in kilojoules per mole, we could, because we're given 1 kilogram of propane, right? So we can actually say kilogram. Well, so this would be a conversion factor, right? So we can convert this to moles, right? Technically kilograms to grams and then grams to moles. But then, yeah, once we get moles, then we can see how much heat is released. Okay. But evidently we don't even have this, right? So we actually have to find the enthalpy, or rather heat energy, that this burning reaction produces. That is where other data comes in for ALEKS. Okay, this is where I just realized I'm running out of time. I think we're good. All right, so this is where we get the, well, they do give us density. That might be useful, I don't know. But notice one thing is they do give us the formation enthalpy of propane, okay? And it says any other data you might need should be taken from the ALEKS data tab resource, okay? So what I'm thinking is this equation, or I shouldn't just say this equation, I gotta explain it. So there is one equation that you should be aware of, and this deserves bringing it up. Let's type something else. This is also in your textbook and your notes as well, of course. So pretty much this one. Well, okay. So here's a good one. So this states that the enthalpy change of an actual reaction can be found by multiplying the stoichiometric coefficient times each product's, it's kind of a mouthful, to be honest. So first of all, sum, that really just means, this really just means sum, right? Okay, so there's multiple products. Let's just focus on one. We'll take the sum of these. So we're going to take the sum of the N times the delta F naught for, that's like standard state. Okay. I feel like I'm explaining this a little too much in detail. I'm just going to try to simplify this. Okay. We are going to take the sum of each one of these, which is the stoichiometric coefficient of that thing in the reaction, the substance, the compound or atom, times its enthalpy of formation of that actual product. Okay. Then we'll subtract the same process for here. Okay, so it seems like a lot, but it's really not. I'll explain it. So let me write this formula down, and then we'll be good. Don't worry about the little O's and knots. That's just fancy. I know I just said don't worry about it, but here I am writing it down. Okay. So, oh, let me go back. There we go. Is it a little blurry?
No, it's good.
Okay, I know sometimes. Oh, we could zoom into that. Helps. There we go. All right, so here's the equation. That's delta. First of all, we do need the delta HF for each thing in the reaction, right? Okay. So one thing I will tell you is the enthalpy of formation. Really, enthalpy of formation is just saying you take two elements to actually combine, or two or more elements to actually combine them just to make these. Okay, and that is associated with its own enthalpy process. That's listed in ALEKS. And also you want the correct states for this, but O2, that's a gas. It's going to be 0. Okay, all the elements, you can't form an element like that's an elemental thing, right? O2 in nature, so you can't form it. It's going to be 0, the enthalpy of it. Okay, and you got to have a baseline anyway. All the other ones do have a value, so I actually have to look those up. I guess I'm an idiot. Let me see here. So, I mean, by the way, they do give us the formation enthalpy of propane at 25 degrees Celsius, right? So that's one thing. So that's what this is. It's given as 103.8 kilojoules per mole. That was in the ALEKS problem. All right. Now we need that for O2. No, that was 0 actually, remember. Same unit, kilojoules per mole. Then we need H2O and CO2. And really these are, the reaction is set up such that I think this is liquid. It doesn't matter though, because they give it to you. These are going to be gaseous, right? Because it's a really hot reaction. Sorry about the marker. These are all gaseous. There. Okay. So we need to find the gaseous water and gaseous CO2 in the data tab. Oh man. Freaking logged out. Sorry. So I'll just go to my student account. Use the data tab. So don't even worry about the thing. I'm just going to use the data tab. It's the same on everything, the data tab. And this is actually completely related to this, by the way. This thing. I'm actually going to sit down. My legs are hurting. All right, so you're going to want to look for the thermodynamic properties of pure substances. And this is what we're interested in, the enthalpy of formation of them. We're going to need to find water. It should be in the oxygen section. I might have passed it. I apologize. I always forget where things are. If you see it, let me know. I'm just looking. There it is. See, oxygen O2 gas is 0. Okay, we're not dealing with liquid. This is all gas. So it's actually negative 241.8. Let me write that down. Okay, CO2 is going to be up here somewhere. Sorry about this. Oh, CO2 liquid gas. Yeah, don't worry about these other values. That's for Chem 2. This is for here, negative 393.5. Okay, same units, right? Because they're all kilojoules per mole. Okay. Let's get back to business. All right. So we can use this equation to find the enthalpy of this actual reaction. How it's set up is like this. So we're going to take the sum of the n is the coefficient. So notice this is products, right? So this is products. These are the reactants. Okay. So the products is going to be gaseous water that's 4 in front of it times the negative 241.8. Okay. And then it's saying take the sum of all of these. So there's one. So now we have to sum the other one, which was CO2. Okay. CO2 is 3 of them coefficient times negative 393.5. Okay. Then it says you take, after you've taken the sum of these things, then you subtract all of this. Okay, so we're going to subtract all this and we're going to find the sum of these ones, right? So we're given propanes, which is, first of all, coefficient of 1, and that's negative 103.8 given to us. Okay, now normally we would add summation these, right? But evidently this was 0 as shown to you. So this is really the whole thing. This will be the delta H not, you can say not, that means like standard state or whatever. Be careful when you do this, by the way, that you got to make sure you get the right PEMDAS and all that, right? Order of operations. So let's actually say, so to be safe, you probably want to do it one at a time. So let's say 4 times negative 41. Okay, that is negative 967.2 plus negative 1180.5 minus negative 103.8. Okay. So really that's just kind of a simple matter of putting these into the calculator, right? So let's add these. And really it's also like subtracting, right? Adding a negative is like subtracting. So it's like this minus this. Negative 147.7 minus this. And subtracting a negative is like a positive, right? You're getting rid of negative stuff, you get more positive. So this, when you subtract a negative, you add. And so we're actually going to add these together. All right. So the final enthalpy change, or in the standard state or whatever, is negative 2043.9 kilojoules per mole. Okay. So that is how much heat is released for 1 mole of this actual reaction, okay? Still recording, I think, yeah, okay. Alrighty. Now, we need to use stoichiometry and thermochemical stoichiometry to actually see how much heat is released given 1 kilogram of propane, okay? So let's do that. So we're going to say 1 kilogram to gram. Kilograms go on bottom, grams on top. Remember, 1 big guy gets to 1, then so kilo means 10 to the 3rd anyway, so that's 1,000. Okay. So that's really just 1,000 grams, right? Okay. Propane. So king of the hill, right? Propane. Now we can use the molar mass to go from grams to moles. And we need moles because check it out. We got moles in our thermochemistry, right? So we're actually going to say grams of that will be here. And then we're always, molar mass is always 1 mole based, right? Because it's how much weight is in 1 mole, how many grams is in 1 mole. You just add up propane. So you can say the molecular mass of carbon is 12.011 on the periodic table times 3 plus 8 of the atomic masses, or atomic mass of hydrogen. So these are both atomic masses. So 1.008. Okay, that's propane. 44.097. Okay. Sorry about smishing them together. It looks funny. All right, grams cancels anyway. Okay, now here's the thing. This is where we actually see how much heat is released by 1 kilogram of propane. We use this fact that 1 mole releases this much kilograms of heat. We don't have 1 mole. We have 1 kilogram. That's probably not a mole, right? So let's actually go ahead and say, let's use that factor. So the fact that 1 mole of C3H8 releases 2043.9 kilojoules of heat. And it's negative because it's releasing. Everything's about the system. The system is propane. You burn it, it releases heat. It's getting rid of it. That's why it's saying minus. It's exothermic. Okay. Now, here's the thing. We put 1 mole here, by the way, not just because that was the original definition. Well, really, by definition, there was a 1 in front of here. That's why we put a 1 here. If there was a 2 coefficient here, you would put a 2 here. Okay, so we're using this as our conversion factor. Okay, this. But if the coefficient changes, you have to change the coefficient. It's 1 mole here, so let's keep it 1 mole. Okay. All right, finally. So really, we simply multiply 1,000 times the negative 2043.9. Divide that sucker by 44.097. Alrighty. We find that 1 kilogram of propane will release negative 46350.09 kilojoules. Kilojoule. That's a lot. Kilojoules is a lot, right? That already means the factor of 1,000 kilojoules of energy. Okay. Finally, that is just telling us how much heat energy is released by 1 kilogram of propane. Okay. All right. Now, the final question. What's the max number of balloons we can fill up, knowing that each balloon takes this much energy, heat energy, in joules? Okay. So here's the thing. First of all, let's review division real quick. And this is actually necessary because you have to do this. So if I said I have 10 cookies and I want to divide them equally by my 2 friends. Okay. Each friend will get 5. That's 5 cookies per friend, right? Okay. So that tells me how many friends, if you will, I could distribute to my cookies. That tells me how much of this I can put into here. I can do that 5 times. Okay. Again, how much of this I can fit into here is 5. I can fit 5 of these into here. Okay. That's what we're going to do here. As it turns out, now here's the thing. You're probably like, wait a minute. So we need this. We need the heat energy that the air absorbs to base our calculation off. Well, guess what? Remember, not only, first of all, at constant pressure, which is atmospheric, it's outside, delta H equals Q. Okay, so that's one thing you gotta realize. So we're good on that because we found delta H, right? So this is all related. Q of the air will be the same as, so Q of the air will be the same as the heat energy that the air absorbs will be the same as the heat of the propane that is released. Okay, does that kind of make sense, Natalie? Like, because we're burning the propane, all that heat energy from the propane is directly going into the air. Does that make sense?
Yeah, kind of.
Kind of. Okay. Well, I don't want to say kind of. I mean,
Fine. I get it. I don't know. I think I'll be fine, to be honest.
okay. No, I'm sure you are as well. Just I know sometimes I say kind of when I know it. So. Okay. Well, thank you for being honest anyway. Alrighty. So we got that. Let's go ahead and actually finish this problem, right? Okay. We do know that this is the heat released by propane, or rather, excuse me. So in order to find the max number of balloons, we need to see that one balloon actually takes this much heat energy, right? So first of all, let's go ahead and convert this value to joules. So remember, you just multiply by 1,000 because it's kilo. You could go through the steps, right? Give the big guy the 1. Kilo means 1,000. This is going to be a huge number. Let's use scientific notation. Let's move the decimal back. 1, 2, 3, 4, 5, 6, 7. 4.64 times, sorry. Okay. That is how many joules 1 kilogram of propane releases, right? Okay. We are curious to see how many balloons we can fill by burning the 1 kilogram of propane. So 1 kilogram of propane gives us this many joules of energy, right? Which is a little bit more than what it actually takes to fill up the balloon, right? So it's like you know, you're doing a recipe for cooking, right? Sometimes you got more ingredients than you actually need to make your salad or something. I don't know. I'm just trying to make this relatable on some level. So really what we're saying is, you know what? Let's actually let's actually divide these. And the reason why is because remember, with this analogy, it's like saying I can fit two of my friends into, I know it sounds weird, but I can fit 2 into 10. It's like saying, how many times can I fit 2 into 10? Or rather, how many times can I fit the smaller one into the bigger one? Well, that's 5 times. Same principle here. We have how much it takes to fill up the balloon, the heat energy, and we have how much energy is produced by 1 kilogram of propane. Okay. So what we're going to say to ourselves is to simply divide the heat available by the heat needed. Okay. Okay. And again, why we're doing this is because it's like saying, remember the analogy, the cookie analogy? We're saying how much heat, or rather how many balloons can we fit into all that heat, if that makes sense. Hopefully. I understand if it doesn't. It's a little weird, but. So by the way, does that make sense, Natalie? It's like saying, here's all the heat we have, which is all the 10 cookies available. And we want to distribute those evenly. So we want to distribute all the heat evenly to the heat that's available.
Yes.
Okay, yeah, kind of. All right. So, and it's for balloons, right? These are the balloons. So heat available is, don't worry so much about the negative. We're just dealing with absolutes here. And then that's going to be sorry. Okay. So really you should have a lot of sig figs when you do this. So I'm gonna try to find where my answers were. So I think it's this one divided by, the other answer's up here somewhere. Yeah, this one. Okay, so I get 19. Don't worry about the negative. This was just telling us how much heat. So 19.3 balloons. Okay, so obviously that's a fraction of a balloon, right? And you have to round this down because you can't inflate a fraction of a balloon, right? Okay, you can only have full balloons, no halves or whatever. Okay. So really the answer is 19 balloons. Wow. That was a lot of work, right?
Yes.
Okay. But assuming that you took all these notes, it should be hopefully somewhat reproducible when you do this problem. Okay.
Yeah, my paper's like filled from top to bottom.
What's that?
If my paper's like filled from top to bottom from this question.
Yeah, it's definitely the longer. This is pretty much I already said on the recording, this is definitely the hardest ALEKS problem you're gonna have this semester. So. Okay, well, I'm gonna stop recording and